the products we buy usually comes with a warranty, and there is a warranty period. Warranty period usually is the reliability is relative to specific length of time. From research, we know that the reliability of the products usually have a curve looks like this. This is the curve. And we call it a bathtub curve because it looks like a bathtub. Why is a bathtub? Because at the beginning, when we start to use it, the failure rate can be high. But after a while, the failure rate goes low, and then we have an extended period of time to use it. After a certain time, the failure rate goes up. So a good example is about the cars. The warranty, factory warranty, usually covers anywhere from the beginning to somewhere here. For example, most of the cars have either 3 years or 4 years warranty. At the beginning, first 2 years, we're probably going to experience a lot of small problems or sometimes big problems with the car. And after probably 2 years, and sometimes we call that a break-in time, and etc., etc. Well, break-in times does have other meanings, but in terms of failure rate, after a certain time, the failure rate goes very low, becomes very stable. For example, for the family cars, what do we call that? It's not SUV, a minivan, right? Minivan, after usually 8 to 10 years, no matter who built it, no matter what the brand is, the failure rate will rise up sharply. SUVs probably have a longer time from the beginning to this point. That means SUV are newer platform. They usually have longer lifetime with lower failure rate in this period. Minivan is an older platform, usually after 7 or 8 to 10 years. It's a good time to get rid of it. Why? Because the failure rate goes up sharply, and the maintenance fee cost will be very high, and it's not economical to keep the car. In order to study those either the bathtub curve or the failure rate, we need to use distribution, and not the probability distribution. And there is a key parameter we're going to use, actually used by most of the products we see in the market, is the mean time between failures. Okay, let's look at an example. One popular distribution of a lot of products has a failure rate with exponential distribution. Exponential distribution, in terms of the curve, looks like this. And the x-axis is time. Okay. The y-axis is the probability density function. So where is the reliability anyways? The reliability is the size of the area under this curve, okay, and above this x-axis. So the size of the area is the probability. For example, the probability of no failure before a certain time t is the size of the area that highlighted in green. So we try to measure the size of this area, and here's the formula. the size of the area is e to the power of negative t over mean time before failure, where e is the natural number equals to 2.7183. So E is defined as 2.7183. E is just another name for this number. We use in the mathematics and statistics in a lot of places. Okay, T is the length of service before failure. Now let's look at an example. Let's say we go to the market, we buy a vacuum cleaner. Okay. On the description, the manual says the reliability of this cleaner is exponentially distributed. The mean time before failure is 4 years. So we want to know what's our chance that this product will die after 4 years. So the highlighted area under this blue curve above the x-axis, the size of this highlighted area is the chance that this product will die after 4 years. Let's continue our example. For the same vac cleaner, same mean time before failure, we want to know the chance that this cleaner will, the life of this cleaner will end before 4 years. So it looks like this. Okay, so we want to find the size of this area. Here comes a little bit about probability. We first, from the table, we know that if t equals to 4, then the size of the area goes beyond t equals to 4 years, which is our the last example. The size of this green area equals to 0.3679. So if you are not sure about this, you can go back for the past 3 slides, go over it again, you will find that. So this size of this area equals to 0.3679. And from the probabilities theory, we know that the whole area under this curve above this x-axis equals to 1. Okay, under this curve, above this line equals to 1, and we know part of it equals to whatever number. Here is a 0.3679. So this area equals to 1 minus the size of this area. So here, this area equals to 1 minus of this area. The area goes beyond 4 equals to 0.3679. So the area, the highlighted here, equals to 1 minus 0.3679. Okay, so it's pretty much, if we calculated this, it equals to 63.21%. Suppose we have a equipment and we want to know the availability of it. So means the fraction of time that this equipment will be available to use. So this one equals, the availability equals to mean time before failure over mean time before failure plus mean time to repair. Here's an example. John has a laptop. His laptop operates 30 weeks on average between failures. Then we need to somehow fix it. So the mean time before failure is 30 weeks. It probably take 1.5 weeks to put his laptop back in service. Now we want to know the availability of this laptop. It equals to MTBF equals to 30 over MTBF 30 plus MTR, which is 1.5. The availability of John's laptop is 95.24%.